failure strain of the fiber, I'll repeat myself, the stress in the matrix corresponding to the failure strain of the fiber is sigma m, because that becomes important. Once the fiber fails, there is no way the matrix can carry all the transfer load. That's our sigma m subscript epsilon f star. Sigma cu is the longitudinal strength of the composite. Sigma fu is ultimate strength of the fiber. So based on the rule of mixtures that we already talked about, we can say sigma cu, which is the failure stress of the composite, equals sigma fu, which is the ultimate strength of the fibers, times volume fraction Vf, plus sigma m subscript epsilon f star, that's your matrix stress at the fiber fracture strain, times 1 minus Vf. So just remember the concept. You don't have to remember the equation because it's all in your notes. So if Vf is less than Vf min, matrix is able to support the entire composite load after the fiber breaks. So it's a very small fiber fraction, therefore the fiber, even after the fiber breaks, the composite is able to carry the load. And any additional load will be carried by increasing strain in the matrix. There is no fiber anymore because the fibers have already failed. Okay? If that's the case, if the fibers have already failed, my sigma f equals 0 when epsilon f is greater than sigma epsilon f star. What is epsilon f star? Epsilon f star is the failure strain of the fiber, F for fiber. Okay? So you can say sigma m, which is the matrix, stress in the matrix, which should be equal to the failure stress of the ultimate strength of the matrix. So sigma cu equals sigma mu 1 minus Vf plus Vf times sigma f. Because our sigma f is 0, the fibers have already failed, I will eliminate this term. So I am left with sigma cu equals sigma mu times 1 minus Vf. Okay? So now we will look at it in a different way. If I plot my the two equations we derived, one for small fiber volume fraction, one for large fiber volume fraction, the two equations you will see can be plotted something like this. This one here is sigma mu, that's the failure stress of the matrix, and with fiber volume fraction, on the x-axis we have Vf, on the y-axis we have sigma cu. So it varies from sigma mu to 0 when you have at this point it is 0. Okay? The other equation is linear and it increases with addition of fiber. So these two lines will meet at this point here, and that's defined as Vf min. Okay? And then we define also another volume fraction here, which is V critical. So V critical is the minimum amount of fiber volume fraction beyond which any addition of fiber will give you actual benefit. Here below this, no matter how much you add fiber, it will not really help. Only once we cross sigma mu, only then you can gain with the addition of fiber. Does it make sense? So, but remember, these two volume fractions are very, very small. You are highly unlikely, or highly unlikely it will govern our design. But that's what it is. So once you rearrange these terms, you get Vf equals Vf critical equals this, sigma mu minus sigma m subscript epsilon f star over sigma fu minus sigma m subscript epsilon f star. So that's one of the equations. And the other one is this is the other one, Vf min. So there are two equations, one for Vf min and one for Vf critical. So those are 2 points, one here, one here. So we have two equations, very simple equations. Once you plug into your Excel spreadsheet, you can almost forget those equations. But in any case, we can calculate our VF min and VF critical based on these two equations. And we have a small example how to calculate VF min and VF critical. I will not go over these numbers, but hopefully today, in another after we finish this session, we'll send you all these files so that you can go over these if you want to. So for this particular example, I have VF min of 0.61%, very, very small, just like in steel reinforced concrete. What's the percent normal you expect in terms of VF min or minimum reinforcement? Steel ratio, it will be very, very small. Okay, what about normal steel ratios you use? What percent? 1% is very good, 1% is very practical, 2 is pushing to the limit, but it is possible, 2 is within the maximum limits, depending on your, of course, steel, FY and concrete strength. Those things will change a little bit, but 1 to 2% is normal. And what will be the minimum? Minimum is generally about 0.3%. 0.3, 0.2, 0.3, depends on, yeah, that's about the range. You will get your minimum reinforcement. So where is 0.2 and where is 1% or 2%? It's a lot of difference. Same thing here. The VF min is 0.61. VF critical is 0.63%. 0.63%. It's not 63%. 0.63%. So our practical range of VF is probably around 40%, 50%, something like that. So it's always going to be very small value. Now I will not go over all the items of interlaminar shear, transverse compressive strength. All those things are important for other applications, but for structural engineering FRP bars, we don't have to go into those details because it will take up a lot of time. Normally I spend about 1.5 weeks, that means about 4.5 hours of lecturing just for micromechanics. So we do a lot of examples and stuff like that. We will not do that here. It's too much. It's not fun for me or for you to read the slides that are having equations. If I write, it's a different thing. So we'll not do that. So in general, factors affecting longitudinal strength and stiffness, of course, yesterday somebody mentioned this misorientation of fiber. Up to 5% you can prove by ply mechanics. You can prove that if your fiber is out of alignment by 5 degrees, up to 5 degrees, it will not make a major difference to the properties of the composite. So misalignment is always a problem, but at the same time, up to 5 degrees of misalignment is acceptable. However, remember that once we place our fiber and we add our resin and the polymerization starts, it's irreversible, therefore you cannot make any corrections after that. And fibers can be of non-uniform strength, the diameters can vary. You saw in this picture there, micrograph, you see a lot of variation in diameter, and there can be other problems. You can use statistical methods. Fiber strength is also dependent on fiber length. So many different considerations. We're not going to go through all of these. And then you definitely remember, if you forget everything else from this micromechanics and processes, that's okay. But remember sizing. Don't mix the sizing. Concrete needs one type of sizing. Composites need a different type of sizing. Sizing is the coating on the surface of the fiber. Okay, so make sure you use the proper sizing. There can be residual stresses because of difference in coefficient of thermal expansion and things like that. So what I will show you is, in the last line I said refer to my notes handout, which we have not sent you yet, but it will be something like this. So it is written up material, so you will see a lot of explanations and stuff like that. So everything is here. If you are interested, you can always look through this, and also any other book, very interesting books we have. So transfer strength and stiffness, stuff like that. You have everything here. If you are interested, you can take a look. And if you are, even for compression, we have some equations, but in civil engineering we don't use compressive strength of FRP, but in other applications they do use. So if you really have to use compressive strength, there are equations for micro buckling and stuff like that. They are all in my notes. But if you are lazy like me, you can do something else. You can write a simple spreadsheet, something like this. So all the equations are plugged in, and you just change these numbers and you get all your mechanical properties. Every single one of them will be right here. Okay? So I'll ask Dr. Das to send this also to you, this Excel spreadsheet. I locked all the cells except for these yellow cells. My convention is all these yellow yellow cells are where I enter the data. Calculations are blue, some are brown. So you don't have to enter anything other than these yellow cells. So you want to play with that, no problem. You'll get all the values. They're quite reliable, I think, but there can be mistakes, so don't take it for granted. And if you are trying, I locked the cells, so it's protected. You won't mess up anything. You just change the numbers and that's it. Okay? Now, what time is it?